My name is Ruth Misener, and I'm part of the Computational Optimisation Group in the Department of Computing. I myself am not an expert in an MPC, and so what I'm doing is I'm presenting computational mixed integer nonlinear optimization. Hopefully this will aid conversations at the conference itself. I'm going to talk about developing spatial branch and bound solvers. And let's begin with talking about my definitions for what I'll talk about here, and also solver software. So mixed integer nonlinear optimization, or MINLP, is very difficult to solve. This quote from 1979, I could say it today as well. What I will assume is that I can write down the equations in my MINLP problem. None of the functions that are here are so-called black boxes where I can only query a function and then maybe get out what is the function value. Instead, I have the entire functional form. I know if each of the f, h's, and g's are nonlinear. I know if there are exponential terms or if there are polynomial terms, etc., etc. So what's going to happen in this minimization problem is that we're going to search over the continuous variables x and the discrete variables y, and I'm going to assume that all of the x's and y's are bounded. Okay. So first off, it's worth it to say, how are we going to represent MINLP on a computer? There's a lot of so-called modeling software, where basically what happens is that it's mathematical software that I can basically write equations, and then each of these solver packages that I'm illustrating at the top will then send the optimization problem to the solver software. So what we will focus on today are specifically the solvers and what is the technology behind the solvers. So here's a very wide array of solver software. The solvers that I've highlighted here in red will manage non-convex nonlinearities to global optimality. So it's worth it to situate this presentation in the literature. I will assume that everyone listening to this presentation knows a bit about mixed integer linear optimization, nonlinear optimization, convexity, and branch and bound. I will use deterministic global optimization as a synonym to MINLP. A subclass of MINLP that's very, very important that I will not cover so much is convex MINLP. This is when all of the nonlinearities in the problem are convex. And then the methods that I'll talk about today fall into the set of complete methods. These are methods that if computations are exact, then you're guaranteed to reach a global optimum within a given tolerance in finite time. So it's worth it to say what is challenging about this particular class of optimization problems. So in the upper right-hand corner, I'm giving 4 constraints. So imagine that these 4 constraints in just 2 dimensions are the constraints of an MINLP. What these constraints say is stay below this red line, stay to the right of this red line, stay to the left of this red line, and stay above this red line. In other words, the constraints say to stay in these 2 red regions. Okay, if I don't know how to solve over this particular space, and really I don't, then what am I going to do? Well, what I ought to do is I ought to develop the so-called convex hull of this feasible space. That convex hull is the smallest region that is convex and includes the entire feasible space in a new optimization problem. So what has happened is I've made the feasible space bigger. So all I have to do is calculate the convex hull of my feasible space. The problem is that's not so easy. All right, so let's go back to our original constraints. And now let's start thinking about what would happen if I develop a relaxation or a convex relaxation of each one of these individual constraints. Let's say instead of staying below that first red line, instead I'm going to stay below this blue line. That blue line on the variable bounds is the tightest representation of that particular nonlinear constraint. Similarly, I would stay to the left of this new blue line. Again, that blue line is the best convex relaxation of that particular constraint on the box. Stay to the left of this blue line and stay above this blue line. So what you can see is just by taking the convex hull of each individual constraint on the box, I got a relaxation that is much weaker than this convex hull that I actually was looking to achieve. So even if I'm able to develop the convex hull of each individual constraint, I am not developing the convex hull of the entire feasible space. That's already annoying. But there's really no guarantee that I'm going to even be taking the convex hull of each individual constraint, because that's a difficult thing to do itself. What happened there is that this was based on how big this box was. This was based on sort of knowledge that x1 was, say, between 0 and 8, and x2 was between 0 and 5. What if I didn't have that knowledge? What if some reason, but instead of knowing that x2 was between 0 and 5, I only knew that x2 was between 0 and 20? Well, then instead of having this nice blue four-sided figure that's dark blue, I would have instead had my relaxation be this cyan figure that is quite big indeed right here. So what I'm emphasizing here is the importance of variable bounds on being able to develop a good convex relaxation in MINLP. Next, let's mention the importance of branching decisions. So as in mixed integer linear optimization, we're going to develop a branch and bound solver. And let's say I developed a branch at x1 is equal to 4. This would be a brilliant branch for this particular optimization problem or for this particular feasible set. What if instead I wasn't so lucky and instead I ended up branching on x2 is equal to 1? Well, what you can see is that even if I was intelligent enough to get the convex hull of the new feasible sets, which, as we've mentioned before, is not an easy thing to do, I still wouldn't get that much of an improvement. There would still be this big blue space in the middle that I would have to search over. So where my branching decisions are is very, very important. Primal heuristics, that is finding where are good solutions, is also very challenging in this particular space. So far what we've done is we've talked about what's challenging with respect to this particular type of optimization problem. Now let's talk about what people do with respect to data structures to try to be able to manage the difficulties in these type of optimization problems. First, let's talk about a directed acyclic graph. Most solver software is going to use a directed acyclic graph internally to basically keep track of how the optimization problem is set up. And so how this is going to work, for instance, is let's say we're minimizing over 3 variables, x1, x2, x3, and I want to minimize over the sum of those 3 variables. Okay, I've got x1, x2, and x3 saved. Then I have some sort of summation operator into which all of those variables go, and that is my objective. Then I have this log constraint that incorporates variables x2 and x3, sums them, takes the log. That's my first constraint. And then I have another constraint that basically does a number of other operations. One of the things that you'll notice here is that in a directed acyclic graph, we're going to reuse structures as much as possible. So for instance, both F1 and F2 share this x2 minus x3 term, and they share this node as well. What we also are going to tend to do is use these hard-coded expression types. And basically what's going to happen is that these hard-coded expression types are going to be items that we can manage automatically with our solver. So for instance, we'll have an objective function, we'll be able to handle division operators, product operators, sum operators, and then we'll be able to manage a whole number of unary function operators. Another data structure that is quite common in MINLP is an undirected graph. Sometimes these undirected graphs are weighted, and this is particularly for quadratic optimization, which has a number of extremely important applications within MINLP. It's actually so important that people usually have a special separate data structure for the quadratics. Basically what happens here is that what you do is you take any quadratic functions and you make a graph. The vertices are the variables, the edges are the bilinear terms, and when people include weights, the weights are the coefficients that link a bilinear term together. Okay, so far we've talked about data structures. The data structures are the things that we use to store MINLP. Now let's talk about recognizing and exploiting special structure in the MINLP. And our example par excellence is going to be this LMTD function. This is a very complicated looking function that is very important in heat recovery networks. But when you get right down to it, things are actually very simple. This is the function that I've plotted out, and it's really very well behaved. So if I wanted to develop, say, a linear relaxation of this particular function, I could just take some hyperplanes. And then if on the right-hand side, after solving a relaxation of the problem, I ended up at this blue dot, well, then I could evaluate the function at that particular combination of x1 and x2. And I could develop a cutting plane that would eliminate that current feasible solution. So this is actually a very well-behaved function. Now, contrast this important function with the automatic convexity detection rules that we have available to us. So this first type, this tree walking rules, and the Hessian computation, these are the types of automatic convexity detection that are typically used in solver software. And most global optimization software will have implemented these automatic detection rules. But the problem with it is that this automatic convexity detection is brittle. And the example that I'm going to use, again, is this reciprocal of LMTD, and it's not going to be easy to find that we have a very simple convex structure here. So what if we just hard-coded it, said basically, this is a convex form? Well, the problem is that that's brittle as well. Hard-coded rules are easily tricked. What if my rule that I hard-code into my solver knows that this is convex, and then my user does a very reasonable transformation and just says, well, natural log of x1 divided by x2, well, that's equal to natural log of x1 minus the natural log of x2. Well, that's going to completely mess up my hard-coded rule. So am I going to have to also hard-code this rule and think about every variation that a user is going to give me? Well, even that's not going to be enough. Because legacy code is often going to assume different numerical strategies. A possible solution I'd like to think about is something that's called disciplined convex programming. So in this particular approach, problems are convex by construction. So what happens is that we impose a set of conventions or rules. You've got this atom library that are the convex functions. You recursively apply the expression rules, and then you allow a user to add new atoms to the library. So what I'd like to propose, and what I think is really exciting, is a hybrid between automatic detection and disciplined programming. So what we've developed is we've developed this software that we call Suspect. And basically what Suspect does is that it detects special structure for Pyomo problems. Remember that Pyomo is an algebraic modeling language that will model MINLP. So what Suspect is doing is that it's extending convexity and monotonicity detection with a plug-in based architecture. And just as an example of Suspect, let's go back to our function that looks difficult, but is actually very straightforward and easy to work with. What we're going to do inside of Suspect is that we're going to register the detector using setup tools. And then what we're going to do is that we're going to register the rules for the convexity detector. We're going to implement the rules returning convexity and monotonicity information. But now let's talk about structure beyond convexity. So in particular, what we're going to do is we're going to talk about the pooling problem. So what happens is that we have these inlets these inlets have known species concentrations. The inlets combine in intermediate storage nodes, or pools, where we're going to combine the concentrations of things. And then we're going to have these output species that have to follow requirements or laws. What you end up in this particular optimization problem is you end up with basically concentrations times flows, and you end up therefore with these non-convex, nonlinear terms x times y. These are sometimes called bilinear terms. If we go beyond these local structures, and now we globally detect the structure of the pooling problem, so that now we're looking at the entire network, well then what we can do is similar to what the mixed integer linear optimization community has already done with respect to network optimization problems. And in particular, we can develop branching strategies, primal heuristics, and cutting planes that are all specifically relevant to this particular class of problems. So what we're doing is that we're proposing a sort of disciplined programming that develops structure beyond convexity. In particular, this would be relevant in things like gas networks, power grid problems, and then there are an array of other really interesting problems that have very special structures. Now it's worth it to start thinking about what are the components of the branch and bound algorithm itself. This is the meat of the solver. The first thing that happens is we've got to think about relaxations. So what happens is that for each one of the sort of special equations that we have understood are going to come into the MINLP solver software, we're typically going to have a recognition of these functions, say for instance a quadratic function, a cubic function, et cetera, and we're going to have developed relaxations for each one of these common functions. So that's common to every piece of solver software, or most pieces. And then what's going to happen is that we're going to recursively compose these functions. In the auxiliary variable method, what happens is that each time we run into an expression that we know how to handle, we basically add a new variable. So for instance, if we did not know how to manage this reciprocal LMTD function, which we discussed earlier, and we might actually want to manage just as one block because it actually is convex. If we weren't able to recognize it, what we would do is we would develop a variable 1 that was equal to the x1 divided by x2. We would have a relaxation for that variable 1. We would develop a variable 2 that was equal to the natural log of v1, and again, we would develop a relaxation for that, et cetera, et cetera. So this is the auxiliary variable method. Another way of recursively composing the functions is to propagate subgradients. There are a number of other relaxation schemes. There are hierarchies for polynomials, sum of squares, et cetera, et cetera. I don't have time to manage and talk about all of those. Now, the goal with all of this is if only we could use all of these relaxations at once. So these are two of my very favorite papers, and what they basically say is any relaxation you have available, you should be using. All of the relaxations that I've talked about so far are over boxes. And one of the things that I'm most interested in right now are in convex relaxations that are beyond boxes. So this discussion really started about 15 years ago when Tardello was talking about these edge concave functions where you only need to sort of know the vertices and then you can develop a relaxation. But this has really exploded in recent years to include quite a number of different cases. To my knowledge, these are not so much in global optimization solvers at this point. You know, each solver might have implemented one or two of these. But what the MINLP solvers need is they need generic data structures to be able to manage all of these new relaxations. And this is actually the reason that I'm most excited to be giving this particular presentation at an MPC, because you all actually have had this particular challenge for quite some time. And for example, the multi-parametric toolkit that you all have is basically something that I think offers us some hints with respect to how we could implement this kind of thing. Okay, so we've talked about relaxations. Now let's talk about branching decisions. The really interesting thing about branching in MINLP is that you're not necessarily going to cut off the current feasible point. And this is one of the nasty examples. So in this non-partitionable set, again, I can be in S1, S2, S3, and then this sort of convex enclosure around S1, S2, S3 is the convex hull of the shape. Now let's say that my relaxation point is this XL right here. Now, there is no way that you can do a single branch and eliminate XL. So for instance, if I said now my branch is either going to be that I'm going to be in S2 or not in S2, well, if I'm going to be in S2, I certainly have from one of the two branches, I've eliminated XL. But from the other one of the branches, if I was to develop the convex hull between S1 and S3, what you'll notice is that point XL still falls in the feasible set between S1 and S3. And indeed, if you're going to do binary branching, that is that you're only going to have a split between two different choices, there is no way in one step to get rid of this point XL. More prosaically, how shall we branch? First off, remember that in MINLP, we have integer variables. And there are these really great MIP solvers that have been developed over the years. One thing that we could do is that we could integrate directly into a MIP solver. So basically, the MINLP solver could be directly inside the MIP solver. We could leave the discrete variables to a state-of-the-art MIP solver. We could say, we don't feel like developing a state-of-the-art MIP solver, so we'll just pass subproblems to them. Or we could effectively develop a MIP solver together with an MINLP solver. In addition to branching on the integer variables, with MINLP, we will also be required to branch on continuous variables. One of the most common strategies in MINLP right now is something that's known as reliability branching. And basically what happens in reliability branching is that you say, okay, to begin with, I'm going to do something that's called strong branching, just because branching is so expensive. I'm going to try branching on maybe X1, see what happens. Try branching on X2, see what happens. Try branching on X3. And then of X1, X2, X3, which is giving me the best improvement to the problem with respect to some metric? So which is improving the objective value the most or something like this? Well, let's say I'm going to select to branch on X3. Okay, now I'm going to think about maybe branching on X1 and X2. Now, this seems kind of crazy because this is a quite expensive operation to do, this strong branching. But what's advantageous about it is that when I'm going to do my strong branching, I'm going to early on get a tree that's going to be relatively small, but giving me big improvements. Once I've done the first few nodes of the branch and bound tree, I will continue on to this kind of branch and bound method where I just keep doing binary branching and just sort of come what may, that's how I'm going to go. And one of the things that I'm most excited about right now is this idea of branching to get a disjunction. If and when they're able to branch to get this disjunction, then you eliminate all this sort of white dotted space from consideration, which is really nice. Bounds tightening is extremely important in MINLP. I mentioned earlier that good variable bounds mean that you can develop good relaxations, basically because these good relaxations are based on variable bounds or the boxes. So there are two types of bounds tightening that people typically use. There's feasibility-based bounds tightening and there's optimality-based bounds tightening. Another item that's extremely important to get good solutions early on is primal heuristics. And in particular, I recommend you to two really excellent works if you want to know more about primal heuristics. What I have learned from these Jedi Masters is that you ought to fail fast, that's the big idea with primal heuristics. So now let's move on to challenges. I've talked a lot about sort of current research in the field, but I want to mention a lot of the challenges that we as an MINLP community have. For convex relaxations, we do need to move beyond boxes. We need to think about auxiliary variables, and we need to think about managing symmetry. For branching, we have to think about branching to get disjunctions. This is an area I'm quite excited about. Bounds tightening, we have to think about incorporating multiple constraints. and thinking about tighter integration with convex relaxations or branching. So I'm really interested to hear anybody's questions from here. I'm also interested in just sort of starting a dialogue here. And so my question is, what's missing on this list? Anything here easy to manage? You'll definitely make my day if so.